Hello students. In this video, we are going to be covering units of measurements and significant figures and how to do calculations using significant figures. This is going to be really important for you to know these rules because it'll help you be successful both in my lecture as well as your lab class. So the first thing I want to cover are SI units. These are used globally, and they refer to the standard units of measurement for different physical quantities. For example, we'll use the joule for energy. Sometimes we use calories. The mole for amount of substance. In the lab, you guys will use grams, and sometimes convert to moles depending on what you need to do. Temperature is Kelvin, not Celsius or Fahrenheit. However, in the lab, your thermometers usually measure Celsius, so you learn inner conversions there. Length uses meters, and this is good because it works with the power of 10, and mass is kilogram. Okay, so we're going to use prefixes for some of these SI units, such as kilo or centi or micro or nano. The reason is in chemistry, sometimes you're using really large or really small amounts of substances or measurements. So I just want to show you that in your book and in a lot of places, you're going to see this sort of chart. For example, centi, for example, a cent, a penny is 1 out of 100. That makes up $1, is 0.01. So it's saying that when you have centi, you're going to have a small, that's going to represent a small number. A centimeter is smaller than a meter. Kilo is bigger. Kilo stands for 1,000. So what that means is 1 kilometer equals 1,000 meters. When you get to milli, 1 milliliter, for example, equals 0.001 liters. I just emphasize this because I don't want you to think that 0.001 milliliters equals 1 liter, because that's not true. So sometimes this is kind of confusing to look at these kind of numbers and exponents. So I found over the years it's easier for students to use these more intuitive relationships. For example, 100 smaller centimeters is or fits into 1 meter. 1,000 smaller millimeters is equal to 1 meter. 10 to the 9 or a billion nanometers is 1 meter. You can use these, and I recommend this. We're going to do what's called unit conversions. I recommend using this page to help you do these conversions. The other thing, this doesn't just apply to meters. You get the same sort of pattern and just swap grams or liters for the meters. For example, 1,000 milligrams is 1 gram. 10 to the 6 microliters equals 1 liter. Okay, we use scientific notation because it's more convenient, because we do use very large or very small numbers. The width of a human hair is 0.000008 meters. That's a little too tedious to write out even. So we say 8 times 10 to the minus 6. It's 8, and times 10 to the minus 6 means you actually divided by 10 to the 6. Instead of saying this many miles between Earth and Mars, we say 3.39 times 10 to the 7 miles apart. So it's literally times 10, 7 times. To write in scientific notation, which you'll have to do, you want to take a number and move the decimal place so you have 1 integer before the decimal. Don't put 2. Don't write 12.34. You're going to write 1.234. And if you started out with this number, 1,234, your decimal was at the end, right after 4. So you would have moved it 1, 2, 3 to the left. So if you moved it 3 to the left, you need to account for that by timesing by 10 3 times. You're multiplying by 1,000, 10 times 10 times 10. So if you have a big number, your exponent better be a positive number. If you have a small number under 1, 0.004560 grams, you would move the decimal 1, 2, 3 to the right. So you get 4.560. Notice that last O is significant, and I'm going to capture it in my scientific notation. But since I moved my decimal 3 to the right, I better divide by 10 to the 3 or write times 10 to the minus 3. You don't just need to write scientific notation. You'll be able to calculate things through multiplication and division. When you multiply, you add exponents. You could do this in your calculator as well. Get practice, I would practice both. But if you multiply exponents, if you multiply psi notation numbers, you add exponents. So for example, if I had a number 2 times 10 to the 4 meters times 3 times 10 to the 3 meters, what do I get? First, I multiply the big numbers. 2 times 3, I get 6. Then I add the exponents. 4 plus 3 is 7. So my final answer is 6 times 10 to the 7. Try it in your calculator. Make sure that works for you there as well. For a division, you subtract the exponents. 4 times 10 to the 2 divided by 2 times 10 to the 4. I would divide the big numbers. 4 divided by 2 is 2. And then I would subtract the exponent numbers. 2 minus 4 is a minus 2. My final answer is 2 here times 10 to the minus 2, which makes sense. This is a number less than 1 because you have that negative exponent, and you took a smaller number and divided it by a bigger number. Measurements that you guys will take in your labs are limited by the instrument that you use. There's some instruments that are really, really nice and you have a lot more digits to read out. For example, an analytical balance has more digits, usually 4 digits after the decimal point. So if I weigh this beautiful butterfly that just happened to fly into my balance, I can weigh it at 0.2735. But if I only had a top loading balance, that only measures to 2 decimal places, so it would have cut off. It would have only recorded 0.27. So I lose valuable information. What do you want to do when you make measurements? You want to record all the digits you see. That's valuable information that the instrument is giving you. So I would have recorded 0.2735. I would never have recorded anything less than that because that is what I want. Precision in measurements is when a lot of the measurements are really close together. And you may have poor accuracy though. Accuracy is when the measurement is close to the true value. You may or may not know what the true value is. But for example, good accuracy would be hitting around a bullseye pretty closely with a bow and arrow. But maybe all of those arrows aren't like really precise next to each other. But high precision could be they're all really, really close together, but maybe they're all off away from the bullseye. This could be due to a miscalibration of a balance, some other miscalibration of glassware, maybe some random error or human error that you're consistently doing that's off as well. Significant figures, I already mentioned you want to record all the digits, and you'll use sig fig rules when doing a calculation. I'll be going over those. The more significant figures you have, the greater the certainty. So let's say you're in the lab and you're using a graduated cylinder and you need to write down what volume you have. What is this measurement? What you want to do is you notice this liquid creeps up the sides of the glassware. So you want to read the bottom of the meniscus. Look at the gradations here. You go from 20 to 30, halfway is 25, and each of these lines must represent 1. 21, 2, 3, 4, 5. So I'm at 25 here. So I'm somewhere between 25 and 26. What do you want to write down? Do you write 25? Do you write 26, 25.0, 26.0? You guesstimate what you can. So if I look, I'm definitely above 25, but I'm definitely below 26. So I would estimate, I would say maybe I'm 25.6, and you write that down. And all three of those are significant. We know there was some possible uncertainty in the last digit, but still, you write that last one down because that's valuable information. Just when you're given an actual measurement or looking at one, you want to look and determine how many significant figures there are. All non-zero integers are significant. So this number, 254 nanometers, has 3 sig figs. Leading zeros are not significant because these are just placeholders to tell you that this is a small number. The significant ones are the 1, 2, 3, so this has 3 sig figs. Captive zeros in between, yes, significant. This has 5 sig figs. Trailing zeros are significant only when a decimal is present. So I have a decimal present in this, it's 23.00, so it has 4 sig figs. Sometimes you do a calculation and you come up with the answer 23, but you need to tell the reader that this actually has 4 sig figs. So sometimes it's up to you to put in the decimal and add some zeros to capture 4 sig figs. If you don't have a decimal, only the 2 and 3 are significant. The trailings don't count, so this is 2 sig figs. Just to let you know, if I put a decimal at the very end here, that would make it 4 sig figs. Exact numbers, when you do calculations with sig figs, these do not limit the significant figures because they present no uncertainty. So examples of exact numbers are 1,000 milligrams in a gram, 60 minutes in an hour, or exactly 60 students in a room. Another thing you'll have to do is rounding. Out there are a couple rules for rounding. I picked the simplest one. If the digit removed is just simply 5 or greater, then that preceding number increases by 1. So let's say I have these two guys. I want to round them to 3 sig figs. So that means I want to cut off this last 9. Since 9 is greater than 5, I increase the 7 to an 8. So my answer is 5.38. If I want to drop this 3, it's less than 5, so I leave it alone. I leave the 1 alone. So my answer is 0.241. The 2 rules you need to know and remember throughout the whole semester and for your lab is the addition and subtraction rule and multiplication division, which are 2 different rules. So when you add or subtract, you have to pay attention to decimal places, which means the number of digits after the decimal point. So this has 2 decimal places. This has 3 decimal places, 1, 2, 3 digits after the decimal point. So you're gonna punch this in your calculator or add them. The answer will have the same decimal places as the measurement with the least, in this case, the 2. So here I show it, 2 decimal, 3 decimals, you add them up, you get 40.533. I write out all the digits or a couple after what I think might be the last significant figure. And my answer will have 2 decimal places, the one with the least decimal places. So my final answer is 40.53. Notice that I tracked this last sig fig here with a bar. The reason is if I had to later take this on and do another calculation, I don't want to drop the 3 so early. I want to use it in my next calculation. So I would use the 40.533, not 40.53, if I needed to use this in another calculation. Multiplication, you don't use decimal places, you use the least sig figs. So if you punch in 2.00 times 2.00 in your calculator, you get 4. Your calculator is not going to tell you how many sig figs there are. You need to keep track. So this would have 3 sig figs times 3. Your answer is 4. But since I need to make it 3 sig figs, I make it 4.00. Do this one, pause it, calculate it, and find the answer for yourself. You get 502.392 centimeters cubed, because centimeters times centimeters times centimeters. You're limited by 2 sig figs. So I put a line here. You could just circle it if you want. How do you reflect 2 sig figs? You can't write 500 because that's only one sig fig. You can't write 50 because that's not the correct answer. The correct answer is around 500. You can't write 500 dot because that's 3 sig figs. This is one specific example where you actually have to use scientific notation. Notice I write 5.0. This reflects the number of sig figs. That's a nice use of psi notation to very clearly show how many sig figs are present, times 10 to the 2, which is times 100, matching the 500 answer. Okay, answer these questions, pause, and then I'll unpause and I'll go over them. Expressing this in psi notation, you move the decimal 3 to the right. Notice I kept the last 0 because it has 4 sig figs. But since this was a number less than 1, I better have a negative exponent. So it's times 10 to the minus 3. This problem, do the operation separately. Do the addition first, then the multiplication, then do the final division. If you do the addition, you have to expand this to standard notation to see how many decimal places. This is 10.55, so 2 decimal places, plus this first guy, gives me this answer to 2 decimal places. I put a line, but I did write the last digit to carry on because I have to do another calculation. And dropping it could change the final answer. When you do the multiplication in the denominator, you're limited by 2 sig figs here with the 10 point. So your answer is 0.811 out to 2 sig figs. So now you're done tracking those first 2 operations. Now you're ready for your final division. Don't think about anything but this new final operation. It's a division, so you have to go by sig figs. Now re-look at this number. This has 4 sig figs. This number has 2, so you're limited by 2 sig figs. Your answer ends up being 38 grams per meter squared. Okay, this is where I want to end here, and I will see you guys next time.